Hello everybody and welcome to my talk, Hacking Exploit Development for Bluetooth Low Energy. Let me first introduce myself. My name is Sarah Mada. I'm a security analyst at NSIDE Attack Logic, whereby my main fields are IoT and hardware hacking, web and network penetration test, as well as the Bluetooth technology. A few words to my company. NSIDE Attack Logic was founded 2014 in Munich, where we also have our headquarters. We are doing mainly offensive security, so red and purple teaming, penetration test, as well as security consulting. So, Bluetooth Low Energy. What is this? Do we need this? Is this important? If you have a look at this diagram, which is provided by the Bluetooth SIG, the special interest group, in the yearly market update, this Bluetooth special interest group is responsible for publishing and maintaining the Bluetooth specification. And if we look at this diagram, then we can see that they estimate a total of of over 5 billion Bluetooth Low Energy devices in 2022. And if you compare this to the world population, which is over 7.9 billion people, then probably it's quite an interesting topic. And most of you at least have a smartphone, which I assume to be Bluetooth capable. So, what's about security? We can divide the vulnerabilities in Bluetooth in 4 categories. There are general flaws, which relate to every wireless protocol, as also Wi-Fi, for example. So everyone can send packets over the air. So jamming a connection and denial of service attacks are very easily to realize. The next big problem is our configuration issues. So simplified that, if you do not use any encryption, then it's probably not secure. A big problem for the protocol itself are design issues. In the beginning of the protocol, you might already have heard about the talk from Mike Ryan, with low energy comes low security. So the earlier version did not provide any security in the pairing at all. It's still in the newer versions, which try to, we will come to this soon. Still in the newer versions, many vulnerabilities were discovered and published, and I think the last one was at the end of last year, which I know about. And finally, we have implementation issues, and implementation issues can lead to very serious vulnerabilities. There's one very impressive example, the bleeding bit vulnerability, which was discovered by the Armis Research Lab. And hereby, the researchers detected a heap-based buffer overflow and the handling of advertising package, which lead to code execution and finally could lead to network compromise of the connected Wi-Fi network. I added the sources for reference. So getting started. If you start with Bluetooth Low Energy, you might you have at first the Bluetooth specification, which is a very large document. The Bluetooth specification, the newest version 5.3, is over 3,000 pages large and is quite overwhelming if you start. Nevertheless, we have not the time to dive in that deep today, but I will give a short overview of the techniques we need for the later exploit. After this, we will discuss our attack scenario, have an overview of the Mirage Framework, which I prefer to use for my exploit development, have here some implementation details, and finally we have our demonstration and the conclusion. If you start with Bluetooth, you have at first to know that Bluetooth has its own protocol stack. The protocol stack is hereby divided into host and controller. The host layers are marked here in blue, are regularly implemented in the host operation system or your smartphone, and the controller layers are separated in hardware. So if you think, for example, The easiest example here is if you have a Bluetooth USB dongle, then the controller layers will be implemented in this dongle, and the host layers are implemented in the host operation system. The host controller interface is then implemented or realized via USB. Might also other interfaces are possible. The most important layers for us here are probably the security manager. The security manager is responsible for the security in Bluetooth, mainly for establishing a long-term key and further distributing encryption keys, or, for example, keys for address resolution. And the second layer which is involved in security is the link layer, which uses this previously established key for the final encryption. So we can summarize the connection setup as follows. We have always two, or in the most cases we have two parties in the protocol, the master and the slave device. The master device is usually your smartphone or your computer, and the slave device are peripheral devices, as for example keyboards or smart light bulbs or any other smart IoT product. This slave devices send advertisements to make itself discoverable for the master device, and the master device will then scan for these advertisements, and if this is the correct slave device to connect, then the connection request is sent, and the connection on the physical layers are established. And after this, we have a service discovery. So every slave device offers services for the host, for the master device to use. And if one of both devices decides that it requires a higher security, then the pairing process can be started. So pairing in Bluetooth depends at first on the version of the protocol or of the hardware, which version is the hardware is capable of, and the other factor are in and output capabilities. In and output capabilities are, for example, displays or keyboards. The earlier versions were the legacy pairing, so 4.0 and 4.1. Here we have just works, passkey entry, and out-of-band pairing. Out-of-band pairing, we won't discuss it today because out-of-band is everything but is not using Bluetooth as a protocol. Just works pairing is, as the name says, just works. So the user has no further interaction from the user required. And for passkey entry, at least one device with a keyboard and one device with a display is necessary. So here, the display device will present a pin code. I assume you already know this procedure if you paired a Bluetooth device earlier. And on the keyboard device, you have to insert this pin to finish the pairing process. This legacy pairing is very broken, and I already mentioned the talk, with low energy comes low security and should no longer be used. With version 4.2, the secure connections feature was introduced. Secure connections are based on an elliptic curve Diffie-Hellman key exchange, and also offer the just works and passkey entry pairing as well as out of band. And additionally, here we have the numeric comparison pairing. Numeric comparison means that we have two devices with a display, and in both devices the same pin will be presented, and if the user compares these pins, it verifies that the pins are identical, then the pairing is complete. Here we have to say that just works pairing is an unauthenticated pairing, so the just works pairing has no protection for man-in-the-middle attacks. Okay, so reverse shells are very good in Bluetooth hacking, so we have to do something other funny. And what is widely accepted are these Bluetooth keyboards, and I have to state here that this is not manufacturer related. It's just an example. This flaw relates to the specific service specification. So in this case, the human interface device service. And what we can do here, we can man in the middle such a Bluetooth keyboard and turn the legitimate keyboard into an rubber ducky device. If we do not know what a rubber ducky is a malicious USB stick. If once plugged in the victim's computer, is able to log or inject keystrokes to execute commands. So for our example, we will refer to the rubber ducky language, the Ducky Script, and try to exploit the victim computer with a very simple example, which just pops up the calculator. So to achieve this man-in-the-middle situation, we have multiple options. The first option is, as already stated, we try to use the just works pairing, which is unauthenticated, and man-in-the-middle setup is very easy to establish. For this, the attacker requires two Bluetooth dongles, one for the connections with the slave device and one for the connection with the master device. And the attacker will present to both directions that has neither in nor output capabilities, and as a result, the just works pairing will be used if the devices accept this. The second option is if you say, okay, I know downgrade attacks, I would never connect my keyboard if I do not have to insert my PIN code. Then we have a second option with the human interface device service. In this scenario, we first pair with the slave device, with the just works pairing. The keyboard often does not have the requirement to do an authenticated pairing process. And then we pair with the master, we spoof the device, wait for the master to connect, and allow the passkey entry pairing, because we say, okay, we are a keyboard, we have input capabilities, and as soon as the victim inserts the pin, on the master presented pin to the keyboard, it will be sent to our attacker device as regular keystrokes, and therefore we can use these keystrokes for the passkey entry pairing. So what do we need for this attack? We need two USB dongles. I prefer to use the NRF58420 dongles. They cost around about €10 and are supported by many frameworks and are therefore very flexible. I use them with the Zephyr project. Here we have an host controller interface USB sample, which is at the end Bluetooth USB dongle, then, if you want to say it like this. For the host layers, I like to use the Mirage Framework. The Mirage Framework is very complex, but also very flexible, and therefore does fit the needs for the Bluetooth protocol, which is also very complex. So as the author states, the Mirage Framework is a powerful and modular framework dedicated to the security analysis of wireless communications. The Python framework supports multiple protocols, for example, Bluetooth Low Energy, Wi-Fi, Zigbee, or infrared. And we have a closer look here. The Mirage Framework has several components. There are at one side the core components, which are necessary for configuration, loading, and execution of modules. We have the internal libraries, whereby the Bluetooth Low Energy stack is implemented, for example, and we have modules and scenarios. We will focus on the modules and scenarios today. Modules offer the possibility to implement a specific attack, for example, the man-in-the-middle attack, and can be used by multiple scenarios to adjust this attack to our needs. So we have one module and multiple scenarios and can easily modify this man-in-the-middle attack to our needs. To do so, we have to define scenario signals in the module. That means every scenario signal stands for a packet that the module might receive. In this example, the packet is called say hello. And if the scenario want to override this method or this packet, then it would have to override the hello world method. Additionally, we can control if the module code is executed. So if the scenario signal method returns true, then the module code is also executed. And if the scenario signal returns false, then the module code will be skipped. To create a module in Mirage, we can use the command line option create module. This will create the following template. Here we have two methods which are very self-explanatory, I think. We have init, which initializes the module. Here the most important thing to note are the arguments. So we can pass some command line arguments to our execution. Most important, for example, the target device address and the host controller interfaces which are used by the module. And we have the run method, which is used for the final module code. So since the module for the specific example, so the secure connections man-in-the-middle model, is very large and also complex, and I also had to implement the cryptography for the secure connection in Mirage. We cannot cover this in detail here, but I will give an overview what the module does. So at first, the attacker will initialize both Bluetooth devices, Bluetooth interfaces, and scan for the provided slave device, also for the Bluetooth device address, and tries to connect earlier than our original master device. After this happens, most devices are blocked because slave devices usually are only capable of holding one connection at one time. And the legitimate master is no longer able to detect the slave device. After this, we clone the slave device, wait for the master to connect, and pair with both sides, depending on the scenario and the requirements. After this, the man-in-the-middle setup is complete, and the module is only forwarding packets from master to slave and from slave to master. So we will have now a deeper look into the scenario. The scenario can be created nearly the same way. Here we have three methods: on start, on end, on key. On start and on end are very self-explanatory again. On start is executed when the module starts, and on end is executed when the module ends. And on key is executed if any key on the attacker keyboard is pressed. So, since we want to pass our human interface device keys to lock the final user input to console, and also we have to pass our Ducky Script here. We will do this in our onStart method. The Mirage Framework provides a Ducky Script parser function, which is very comfortable. So we can provide our file here and have 4 callbacks, which I will explain on the next slide. On end can hereby be ignored, it's very trivial. And on key just says if we press the escape key, then we end this module, and if we press 1, we want to inject our Ducky Script to the established man-in-the-middle connection. The best way to explain this method is if we compare this to our Ducky Script. So at first we have the add Keystrokes method, which is most important. So here we have so for human interface devices, it works as follows. So if you press the key on your keyboard, then the signal will be sent for the key, and if you release the key, then the keystroke release message will be sent. And what is most important here is the timing. So if you're too fast, or if you're sending our keys, our messages too fast, then some of our keys will be skipped. And if you're too slow, then the user can see every single letter appearing on the screen, which is a bit obvious. In the packet list just is the array add delay adds the delay, or is for the delay parameter of our Ducky script, and add text is for the text, for the string parameter of our Ducky script. So one last thing to do. Since we want to log our keystrokes, we have to override the onSlave handle value notification packet. In Bluetooth, these keystrokes are sent via notifications from the keyboard to the computer. And here we check for the handle hex 13, and if it's the right packet, then we log our keystroke to the command line. So one last thing. The used keyboard for this example requires the user to push the button on the backside to put the device in advertising mode. So the device is regularly not in advertising mode, but you have to push the button if you want to connect this device. I will get to this point after the demonstration. So I hope to stop this here. Okay. So what we can see here is on the left side is the victim Windows operation system. On the right bottom, we have the Bluetooth keyboard, and on the right top, we have the attacker terminal, whereby the Mirage Framework is called, with the Bluetooth secure connection man in the middle module. We are providing the Bluetooth device address. The Bluetooth device address can easily be sniffed, for example, with the Uber tools, or also with Linux utilities, as for example, Bluetooth CTL. This device, is a funny fact, uses a random address, and the randomness of this device is that the force bytes of the address is regularly increased by 1 bit. So, okay. Then we have our interfaces, host controller interface 0 and 1. We do not require master spoofing in this case, so that the keyboard does not care about who's connecting. But we need slave spoofing so that the computer holds the keyboard for a regular Bluetooth, for the regular Bluetooth device. We provide our scenario, so Bluetooth Low Energy human interface device man in the middle, and finally we provide our Ducky script. Okay. Okay, that's good. At first we are entering the scan stage, so okay, this is very bad, sorry. Maybe I can start. 1 second, sorry. How is this? So maybe this is better, hopefully. Yes, okay. So we're entering the scan stage. Now the moment is here to push the button on the background of the keyboard. After this, the keyboard will be detected, connected, and cloned. And now we are waiting for the master device to connect. So master is connected, man in the middle stage is established. In the background here is now the service discovery that takes some seconds, and now the Bluetooth keyboard is connected. We can check now that our keylogger is working. And this keylogger is also working if the Windows screen is locked, so we can also capture the login password of the user. And finally, we can inject our Ducky script by pressing the 1 button on the attacker keyboard and opening the calculator. Okay, so a few thoughts here. How easy is this? You could say, okay, if this attack is only possible if the devices are not paired. Well, there are many ways to disturb the connection and enforce a new pairing process. So the easiest way I could think of is I just jam the connection, and as soon as the user is annoyed enough to repair his device, I'm able to intercept this connection. The next question is what you can ask yourself: would you push the button if your keyboard is no longer working and repair the device? I think I probably would. And to prevent this attack, you have to make sure that your keyboard provides security mode 1 level 4. This means that the secure connection mode is enforced, so that both devices enforce that an authenticated pairing algorithm is used. So not just works pairing, and then this attack is no longer possible. Okay, that's it. So, questions?
Cool. Thank you very much, Sarah. Round of applause for a nice talk. I think it was really interesting. We have some time for questions. If you have a question, please run to the front, to the microphone, and...
You named it Bluetooth low energy. How much of those attacks also applies to Bluetooth regular energy?
Regular.
Specifically, low energy specification of Bluetooth.
Well, the Bluetooth class specification also has unauthenticated pairing. So it's also called just work. So the specifications are not identical, but the pairing algorithms are comparable. And if your keyboard allows this unauthenticated pairing, then you also have the problem.
You mentioned that specification has 3,000 plus pages. And then if you look, it also has a ton of specifications for profiles and services. And you have different types of operation, mesh, and you have sort of regular advertising and then the authenticated communication. How do you start with Bluetooth Low Energy if you want to do this and do cool things like this?
It's a good question. I think if you start with Bluetooth, then there are some easy tools, as for example, GetHacker or Beetlejack, which you can start with. And I think most important is that you get used to the protocol. So analyze the communication of devices. So very easy to analyze the communication for Bluetooth protocol is via the host controller interface. This is possible on Linux devices via the Bluetooth monitor. You can also extract the host controller interface Snoop block on Android devices. So this is a developer feature. And the benefit in this case is that since the encryption is established in a link layer and you capture the devices on the host layers, then they are not encrypted, and you can check what the protocol is doing. Because if you're sniffing the protocol over the air, which is on the one side very complex and not working very well, then you have encrypted traffic if they're using encryption, and then you cannot determine what is happening there. So the best way is to, I think, is to start to get a device, get the host controller interface logs, put them to Wireshark, and analyze the connection setup and try to find the required parts in the specification. It's not easy, but once you get used to the specification, it also makes kind of sense.
Cool, thank you very much. So we don't really have time for another question, but feel free to reach out to Sarah in the break. I think she will be happy to answer any more questions. Thanks again a lot for the talk, Sarah, and a round of applause.